Lesson 6.4, we are going to make more comparative inferences about populations. So, if you look at the Explore It, Jackson and his brother Levi watched Jewel Geyser erupt one afternoon. They record the time intervals between eruptions. The dot plot shows their data. Jackson estimates the average time between eruptions is 8 minutes. Levi estimates the average time between eruptions is 8.5 minutes. So what we're going to look at here is how we can construct arguments to support each of their positions. So if you look at Jackson's position, he said that it was about 8 minutes. And it would take us a minute to figure this out, but an argument that would support Jackson's position could be that the median is 8 minutes. Okay? So if he estimates that, that to be an average, that's what he's basing it off of, maybe as the median. Okay? Now, we also want to look at how Levi might have come up with his answer. So Levi estimates the average 8.5 minutes. So if we look at the graph here, can you see how he might have come up with 8.5 minutes? So if you notice on this dot plot here, 8.5 has the most dots by it. So 8.5 minutes is the mode, we could say. Okay, so either one of them could have, an argument to why their answer might be right. So there's just different perspectives that we're going to maybe be, needing to look at to decide what our answer is going to be here. Example 1, Quinn collects data from a random sample of 20 7th grade students who participate in a youth fitness program. She compares the number of curl-ups each student completed in 30 seconds last year and this year. What can Quinn infer from her comparison of the data sets? So if we just look at the numbers in this table that they've got, the numbers are not in order. It's pretty much a mess of looking at that and trying to see what's happening. So we could do a frequency table, would be an option. The book went ahead and did a dot plots here. They did separate dot plots. Now, one thing we want to make sure if we're comparing these dot plots, we want to make sure on the number lines what our starting and ending values are. So on this one, if you'll notice, this top line starts at 20 and it goes to 30. The bottom one starts at 20 and it goes to 30. So the starting and ending numbers are the same on both of them, means we can pretty much directly look at these comparing them. Does that make sense? In other words, if the one would have started at 0 and went to 15 and the other one starts at 20 and goes to 30, they're not starting and stopping at the same spots, then we can't just directly look at them and compare them to each other. This case we can, though. They did a good job of making these relatable to each other. So if you look at these, make some observation here. So a couple observations here. The book talks about the mode and the range, which is fine. The problem, sometimes the mode might end up being our highest number or our lowest number. If it's the highest number or the lowest number, that might not be our best representative of the whole set of data. The range is fine. Notice the range is a little bit higher this year than last year, so a little bit more variability, a little bit more spread out numbers. Another thing we might look at is the median or the mean. Compare those as well. And kind of if you just look in general with these two, it looks like in general that people did more curl-ups this year than last year. Okay, not everybody, but definitely it's kind of shifted towards the right this year compared to last year, you might notice. We look at the try it. Quinn also collects data about push-ups. Does it appear that students generally did more push-ups last year or this year? Explain your reasoning. So you might notice again, it looks like we got a little bit more last year towards the low end, this year towards the high end. Once again, double check your numbers. Both of these number lines go from 0 to 12, so we should be okay with that part of it. So here's what we could say, something like students generally did more push-ups this year since there are more dots above higher numbers. Again, nothing earth-shattering here. Just kind of a common observation that we might make. Next question asks, how does the range of these data sets affect the shape of the dot plots? How does the range affect the shape? So if we have a greater range, it's more spread out and it has a flatter shape. If there's less of a range, then that means they're not as spread out. Then it would have a taller shape, or as a student said, it would be more like it's got hills in the dot plot. Again, like a roller coaster maybe, rather than a more level dot plot that we might have if we have a greater range. Next thing we're going to look at is called mean absolute deviation, or MAD. To get a mean absolute deviation, the first thing we're going to do is find the mean. Then we're going to find the distance between each data value and the mean, and then find the average of those differences. That's how this is computed. Now, a lot of the problems we're going to do, we're not actually going to have to work this out. They're going to tell us what this mean absolute deviation is. But if we know how it works a little bit, maybe gives us a little better understanding of what that number is, what it means for us. So what we're going to do here in a minute, we're going to be watching a video from Khan Academy that has to do with mean absolute deviation. One thing when we work this out, after we've done this, is if the numbers are close to the mean absolute deviation will be lower, and if numbers are further from the mean absolute deviation will be higher. Okay? In other words, low mean absolute deviation, there's less variability. The numbers are all pretty close to the mean. If we have a high mean absolute deviation, the numbers are more spread out. We have more variability. Okay, and again, the video we watch with Khan Academy is going to explain that a little bit more visually for you, so you can see exactly what we're talking about. So look at example 2. Quinn computes the mean and mean absolute deviation, or MAD, for each data set. How do these measures support Quinn's inference from the data displays? So you just look at the numbers here. You might notice that the mean or average curl-ups completed this year is higher than last year. Okay, it's 26 6/10 versus 23 6/10, so it's on average people did 3 more curl-ups this year than last year. Mean absolute deviation is 2.1 versus 1.4. So mean absolute deviation tells us that a little bit higher this year means on average there was more variation. The numbers were more spread out this year than last year, is what we can tell by that. Okay, so here the book mentions that the mean this year is greater than last year. Mean absolute deviation is greater this year, which suggests not all students made the same progress. Okay, or again, we could say there's more variation in the number completed this year, which, visually, we look at that, we can see that, how spread out the numbers are this year compared to last year. Example 3, Rafi, one of Quinn's classmates, reported the numbers of curl-ups he completed this year and last year. He did not tell Quinn which number is for which year. Based on the data that Quinn gathered, which number most likely represents the curl-ups he completed last year? So 19 or 23 for last year. In general, last year people didn't do as many curl-ups, so most likely would be that he completed 19 curl-ups last year and 23 this year. Okay, again, basing off of people most doing more curl-ups this year as opposed to last year. If you look at the try it then, Peter surveyed a random number of adults and a random number of teenagers about the number of hours that they exercise in a typical week. He recorded the data in the table below. What comparative inference can Peter make from the data sets? So, looking at our information here, looking at the table, pretty big difference here we can tell off the bat is in the mean. Okay, for the mean, pretty quick to notice teenagers had a lot higher mean for the hours of exercise than adults did. Mean absolute deviation, a little bit higher for the adults. So a couple things we could say out of that then. First of all, we could maybe say that something like, in general, teenagers exercise more than adults. We could be even more specific and say teenagers exercise almost twice as much as adults. And then based off of the mean absolute deviation, we could also say that adult exercise times varied more than teenager exercise times. Okay, so in other words, if we would draw a dot plot, we would see that the numbers for the adults would be a little bit more spread out than for the teenagers here.